Hello everyone, I'm Tian Sun from the Geological Survey of Canada. It is my great pleasure to introduce you today our recent paper published in GRL. We know that the igneous oceanic crust contains many faults and fractures. These fabrics help host the vigorous hydrothermal circulation, affecting fluid, heat, and chemical transport. Studying the distribution of these faults is therefore very important. A standard tool for studying these faults is seismic anisotropy. That is, how seismic wave speed varies in different directions as affected by the preferentially aligned faults. It is more difficult for seismic wave to travel across the fault damage zone, and higher seismic P-wave velocity is typically found to be in the ridge parallel direction as the crust appears to be less fractured. A large body of active source seismic studies consistently show the same pattern, and the degree of seismic anisotropy determined at numerous sites spanning a wide range of plate spreading rate and plate age is typically less than 20%, indicating a moderate fracturing degree of the oceanic crust. In our study, we try to provide more direct determinations of the mechanical properties of the oceanic crust. We use cable-connected, high sampling rate, fluid pressure observations recorded in sealed IODP holes at the Juan de Fuca plate. The two oceanic plate holes penetrate through the sediment layer and are sensitive to the pressure change in the uppermost igneous crust. And for the dynamic ground shaking started here, formation pressure variations can serve as an ideal proxy for the dynamic volumetric strain. And because seismic body wave energy dissipates more rapidly, and the love wave do not cause any volume change, it is a relay wave that is responsible for the pore fluid variations seen here. This dominance of relay wave is supported by the nice waveform agreement between the radial component seismic ground velocity and the formation fluid pressure change, as shown in this example here for this Kermadec earthquake. Besides the waveform similarity, what is more important for our purpose today is the relative amplitude between the two signals. That is, given the unit strain, how large is the induced pressure change? This efficiency in pressurization is essentially controlled by how porous and how compressible the rock matrix is. Let's consider these two scenarios here by comparing them with the reference case. Given the porosity, a softer rock matrix means that pore fluids need to sustain a greater portion of the external loading. Therefore, the pressure change is larger. And given the matrix compressibility, a high matrix porosity means that more fluids are involved in sharing the load, and therefore the net pressure change is actually smaller. This simple pore elasticity analysis provides clues to the oceanic crust mechanical properties. We studied a number of earthquakes around the world, and all those events allow us to derive the pressurization ratio or the pressurization efficiency in different directions. At the two oceanic crustal sites, we found consistent direction dependency, indicating that rock matrix is most compressible in the plate spreading direction. Such direction dependence is not seen at the accretion prism site. With other physical properties of the crust being well determined, we can use the observed direction-dependent pressurization to infer the effective bulk modulus of the rock in different directions. We report a large contrast in the effective bulk modulus by a factor of 5 between the ridge parallel and the ridge normal directions, indicating dense fracturing of the shallow oceanic crust, which is also consistent with the previously determined large hydraulic anisotropy in the same area. The observed compressibility contrast here is equivalent to a seismic P-wave anisotropy of greater than 50%. It is much higher than earlier seismic measurements, and it implies very dense fracturing of the shallow crust. Our study site is in the middle of the Juan de Fuca plate, and there are good reasons to believe the fracturing degree could be even higher in both directions. Closer to the mid-ocean ridge, there's less mineral infill, and open voids may remain open. And closer to the trench, reactivation of normal faults associated with active plate bending is known to occur. These crustal faults and fractures must play a key role in accommodating fluid transport and in hydration of the oceanic slab. Thank you for your attention.